Hi everyone. Today we shall discuss regarding control system, that is model 3, derive the values of static error constants and steady state error for type 0, type 1 and type 2 system for a step input. Okay. So this is a steady state for unity feedback system we are considering. This is a closed loop. So R of S is input and C of S is output, G of S. Okay. The closed loop transfer function is C of S divided by R of S equals to G of S divided by 1 plus G of S. It depends upon the negative feedback or positive feedback. Okay. So here it is negative. So we have taken 1 plus G of S. Here we have not considered H of S because here they have given that unity feedback system. Okay. G of S equals to what we can write here, K into 1 plus ST Z1. Z indicates zeros, P indicates poles. We will come to know in detail in root locus. What is zeros and what is poles? From the characteristic equation, we will find out the poles. Okay. So K into 1 plus ST Z1, 1 plus ST Z2, 1 plus ST Z3. S to the power of n, 1 plus STP1, 1 plus STP2, 1 plus STP3. So P indicates poles, Z indicates zeros. For a unity feedback system, so what you can write E of S, okay, E of S equals to R of S minus C of S. So R of S is input and like this it is, right? This is the summing point. So this is a R of S. Here it is R of S and this is a C of S. So here minus it is. Here minus. So R of S minus C of S. That is the value of E of S. The output of this. This is the E of S. Okay. Next, E of S equals to R of S minus C of S. We have written that C of S divided by R of S equal to G of S divided by 1 plus G of S, right? So that C of S equals to, we can write G of S divided by 1 plus G of S into R of S. So when you take out R of S as common, 1 minus G of S divided by 1 plus V of S. R of S we have taken common. E of S equals to what you can write after taking LCM, you will get 1 divided by 1 plus G of S into R of S. So here ESS is the steady state error. ESS equals to limit t tends to infinity E of t. Okay, so if limit S tends to 0, S into E of S equals to limit S tends to 0, S into E of S value is 1, and that is what we got, R of S divided by 1 plus G of S. This is the standard equation what we call ESS. Okay. This is my notes. You can observe same it is as written from standard textbook. Steady state error of a unity feedback system, have written the closed loop and same G of S, and for unity feedback system E of S equals to, so R of S is input and the C of S equals to E of S. So we have substituted the value of C of S here. So we have substituted the value of C of S. Later R of S take out common. So you'll get the 1 divided by 1 plus T of S into R of S, that ESS equals to limit t tends to infinity E of t. So if you apply the, if you write in terms of Laplace, limit S tends to 0, S into E of S, equals to limit s tends to 0. So E of s value we have substituted. This is the standard equation you remember. Okay, for next. Okay, static position error constant, that is Kp, K suffix P. ESS equals to limit S tends to 0, S divided by 1 plus G of S into R of S. This is the steady state error standard equation. Steady state error of the system for unit step input. This is for unit step error. For unit step input, what is the value of ESS? Okay, so limit S tends to 0, S divided by 1 plus G of S into 1 by S, because unit step input is 1 divided by S. I have substituted. So here S will be cancelled. Okay, so 1 divided by 1 plus G of 0. So the static position error constant Kp is defined by Kp is equal to limit S tends to 0, G of S equals to G of 0. That is what? Kp is nothing but limit S tends to 0, G of S, okay, or it is equals to G of 0. So instead of writing G of 0, we can write it as Kp. K suffix P, ESS equals to 1 divided by 1 plus Kp. That is the steady state error of a step input. Next is static velocity error constant. This is Kv, K suffix V. ESS equals to limit S tends to 0, S divided by 1 plus G of S into R of S. Steady state error of the system for unit ramp input is, that is ESS equals to limit S tends to 0, S divided by 1 plus G of S into 1 divided by S square. So what you will get? ESS equals to, you will get 1 divided by limit S tends to 0, S into G of S can be written as what? This can be written as Kv. Okay, this can be written as Kv. So ESS equals to 1 divided by Kv you will get. Okay, here 1 S will be cancelled. Okay, so what you will get? S into. Similarly, you need to do for acceleration. Static acceleration error constant ESS equals to limit S tends to 0, S divided by 1 plus G of S into R of S. Here the steady state error of the system for a parabolic input. So for parabolic input is 1 divided by S to the power of Q. This is called the parabolic input. Okay. So here this will be cancelled. S square plus S square into G of S. Okay. So this will become 0. So S square into G of S is nothing but a Ka. Okay. ESS equals to limit S tends to 0, 1 divided by S square into G of S. The static acceleration error constant Ka is defined by Ka equals to limit S tends to 0, S square into G of S. The steady state error for a parabolic input is given by a ESS is equal to 1 divided by Ka. But what they have asked here, there are the values of static error constant and steady state error for type 0, type 1, type 2 system. Okay. So now till now we have discussed regarding steady state error. Okay, that is for ramp input and parabolic input and step input. Okay, so now we know the Kv, Ka, Kp. Okay, so type and order of a system. Type and order of a system. If n equals to 0 in the numerator, in the denominator, if n is 0, then there is a no pole at the origin and the system is a type 0 system. If n equals to 1, then it is a yes. So it is a referred as type 1 system. If higher orders, if for example n equals to 2, n equals to 3, like that, the highest order of the characteristic polynomial gives the order of the system. type 0 system. So type 0 system here s to the power of 0, it is 1. Okay, so g of s equals to same as it is, you need to write it, but you need not to write yes. Okay, because here s to the power of 0, it will become 1, k into 1 plus st z 1, 1 plus st z 2, same as it is, you need to write. Next, kp equals to what we have written, limit s tends to 0, g of s into h of s. Now what we are taking is h of s value is 1. That's why here only we have considered the g of s value. Here what you get when you substitute the value 0, 1 plus 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 0, and here also 1 plus 0. So k into 1 divided by 1. So value is 1. Sorry, k. Okay. Next, kv, that is velocity, equals to limit s tends to 0. Here s is there because for kv, limit s tends to 0, s into g of s. Okay. For ka, s square into g of s. Okay. So here s is there, k into 1 plus st z 1, 1 plus st z 2. So here when you substitute here only s as 0, you will get 0 into something, you will get 0 only. So no need to substitute. Okay, you will get the value is 0. Here s square is there. So here only it will become 0. So you will get the answer is 0. Next, type 1. So for type 1, what it will be there? S to the power of 1. So g of s, g of s, in g of s, s to the power s, it will be okay in the denominator side. So for type 0 system, what we got, the first step input, ESS equals to 1 divided by 1 plus kp. So what we got, the value of kp here, k. Okay, that you substitute. For ramp input, what we got the value, kv equals to 0. So 1 divided by 0 is infinity. For parabolic input, what we got the Ka value 0. So 1 divided by 0 is infinity. So you need not to solve from starting. What they asked is derive the values of static error constants and steady error. Okay, first you derive that for type 0 and type 1. Okay, first, so you derive that and you write down this one. Okay. Next, for type 1 system, similar. Okay, type 1 system, S is extra here. Okay, Kp equals to what? Kp equals to limit s tends to 0, k into, sorry, limit s tends to 0, g of s into h of s. So, g of s value substitute. Okay, so here when you substitute the value 0 here, okay, so you will get the infinity. Okay, next, kv equals to limit s tends to 0, s into g of s. So here both s will be cancelled. So you'll get the, when you substitute the value 0 here instead of s, you'll get the value is k. Next, k equals to limit s tends to 0. S to the power of 2 is there. Here s is there. So 1 s will be cancelled. 0 into something, you'll get 0 only. So the value is 0. Now you substitute in the equation, that is ESS equals to 1 divided by 1 plus kp. Kp value is infinity. So infinity can be written as 1 divided by 0. So 0 will come to the numerator. So it is value is 0. Okay. So for ramp input, ESS equals to 1 divided by kV. kV value is k we got for type 1 system. For parabolic input, ESS equals to 1 divided by Ka, that is equals to 1 divided by 0, that is equals to infinity. Next, type 2 system. For type 2 system, s to the power of n. N equals to what? 2 here. Okay, in g of s, here 2. That is s to the power of n. N is 2 because the type is type 2 system it is. Okay. So what will get? Kp equals to limit s tends to 0 into g of s. Into h of s value is 1. G of s value substitute. So instead of writing s, you substitute 0. K, here only s square is there. So you will get something divided by 0 is infinity. Next, kv equals to limit s tends to 0. Yes, here s will be cancelled. One time s will be there. Here s is there. When you substitute 0 here, you will get infinity. Something divided by 0 is infinity. Next, for ka, s square. For k equation is limit s tends to 0, s square into g of s. In g of s also s square is there. In equation also, formula also s square is there. So it will be cancelled. So what you will get is k into 1 divided by 1. So you will get 1 k. Okay. So now ESS for this you need to find out. Okay, unit step input, that is ESS for step input equals to 1 divided by 1 plus kp value what we got infinity, so that can be written as 1 divided by 0, so 0 will become to the numerator. Okay, so for ramp input, ESS equals to 1 divided by kV. So this is also infinity. 1 divided by 0 can be done for infinity. So 0 will come to the numerator, 0 value. And for parabolic input, ESS equals to 1 divided by Ka. Ka value what we got for type 2 system, K. Okay, that you substitute, that is a constant term. Okay. So you can write depending upon the marks. Okay, if they have given for 6 marks, you need to write type 1, type 2, type 0, type 1, type 2 system, and you can solve this KP, KV, KA, and you can write directly steady state error. Okay, if they ask to derive the KP, KA, KV, then you need to derive and you need to do for a separate cases, that is type 0, type 1, type 2. Okay, so depending upon the marks you write. Okay, derive the values of they have asked to derive the values of static error constant, so no need of deriving the kp, kv, ka. Okay, go start with type 0. Okay, I explained now, just for introduction purpose. For a question, for if they ask like this question, so you go with the directly type 0 system. Okay, you can start from here. Okay, type 0. So you can write these things, what g of s and kp, kv, ka. After finding the value of kp, kv, ka, and that you substitute in the steady state error, that is the ESS. Okay, ESS equation, what is the equation for ESS? For a step input, it is a 1 divided by 1 plus kp, and for ramp input, 1 divided by kv, and for parabolic input, 1 divided by ka. That is what? Okay, steady state error and static error constants. Same thing I have written in the notes. Static error constant is nothing but kp, ke, ka, kv. Okay, in next class we shall discuss with the other topics. Okay, subscribe channel for more updates.